Okay, so I want to start off with a bit of background here. Procter & Gamble started the systems engineering program about 4 years ago, and it was launched with a study to assess the benefits, cost, and feasibility of implementing model-based systems engineering capabilities across the enterprise. So not within a discipline I'm talking about, as far upstream as product conceptualization, all the way down through supply network operations, product design, and manufacturing in between. To be able to do that without tipping the scales of complexity to the point where we break the process or start to hurt the existing projects. So that study went well. We determined, in fact, the benefits were real and substantial, and that it was feasible. We've made a series of investments over the past several years in terms of redesigning the work process, redesign our thinking about data, so the systems meta model, the automation to support those two things, and pilots in multiple business functions and across multiple business sectors to make sure that we didn't have a business-specific solution here, that it really was a generic system solution. So what I want to share with you today is a few key learnings, a few tenets, if you will, that surfaced from that work that we think are critical to succeeding in that type of context. And so I'll just enumerate them here quickly, and then we'll go through them as I kind of tell you our story, our journey over the past several years. The first tenet is that we have to shift from a love affair with activities to a love affair with assets. So we need to think about and design the processes to support the asset creation and modification. Secondly, all the disciplines need to really come to grips with and appreciate the fact that a large percentage of their job is identical across disciplines. They're basically there to manipulate systems in the end. Yes, they have domain-specific roles that they have to manipulate as they do that. The fact that there's common things that they need to let go of the differences that are not value-added in their different work processes. And then lastly, probably most substantial, is that we believe to integrate all of these disciplines. We've got over 30 some odd disciplines to go from concept to worldwide distribution of products, that there's one canonical model that needs to describe the intent of those systems and the requirements of those across all the business functions. So those are the key things I want to get across. But in the back of your mind, you're probably thinking, you guys make paper towels, we're like building vehicles and airplanes, there's a difference in complexity. And I'll acknowledge that on the surface, right? You can make one submarine and sell it for $1 billion, or you can literally make 5 billion diapers and sell those for 20 cents a piece to make some. There is differences outwardly, right? And those show up in the organization, and the ecosystem controls our project lifetimes. Ours are much faster cycle time. But if you look at it from a physics standpoint, certainly from a software standpoint, nobody's going to compare to autonomous vehicles, probably planes included too. But from a physics standpoint, we have pretty simple goals. If you're into air or auto, you're trying to transport something. It's either humans or munitions. And for us, we're trying to clean a stain out of your clothes. That's some pretty complicated chemistry there too, right? But the part I think that's more similar that eludes most people, because the delivery mechanisms for our products are hidden from your view. And so most people wouldn't know that that paper towel that you're tearing off the roll there, that was built by a machine that has as many parts as a 747. And as you wrap that baby in that diaper, there's as many lines of code running that diaper machine as in the average military fighter jet. So there's extreme automations, there's extreme physics, multi-physics that we deal with in building these products. And we're trying to stand these machines up and operate them in over 70 countries around the world. So we have a lot of similar problems. It's just that the delivery mechanism for our products tends to be hidden from view versus boarding the plane. We also have similarities in the journey in that we all started with pretty simple beginnings. If you think about the construction of the first airplane, you had line of sight between every business function and the assembly of every part. So if you changed something you were doing, it was quite clear how it impacted the next person and their part as you were assembling the plane. It was right there. And unfortunate for us, we don't control the complexity. The world became a smaller part. Our organizations grew, and it's departments within organizations and sub-departments that create their business processes. And if you read Willie Donaldson's book, Simple Complexity, it talks about some things that happen as they do that, and they don't have the enterprise in mind. They're really trying to make their function work and get repeatable results with the other business functions. And so you inherently end up with a very complex innovation system that is sub-optimized. And we could live with that complexity if the bar wasn't getting raised daily. So every day we get less tolerant, and in fact the probability of cross-discipline transmission errors increases. And the shareholders are less tolerant that if your competitors don't make the mistake that you do, that shows up in the marketplace. In addition, the workforce is turning over more frequently now. There's a tremendous knowledge loss. And so we run a larger risk of losing the basis for why technical decisions were made. And then lastly, as these feature sets get more complicated, as Chris Davey talked about, it's a blur of features. There's so many features being included in every product. The emergent behavior becomes more of a factor, and by definition, emergent behavior doesn't sit in a department. It sits across the departments. And so you have a choice. You can redesign your organizational model and your work processes for every emergent behavior case, or you can redesign your work processes to handle that. You're not going to change your organization. So there's old friends that we also have to keep up with, old problems around making sure that we're in touch with the user's needs, past and evolving, and also that we've maintained the technical knowledge for the new users coming in. And requirements analysis, we have to continue to minimize in these more complex systems, incomplete requirements, incorrect requirements, overly constrained requirements, and then we need to pull forward the trade-off space, the visibility of the trade-off space. So those are old problems. The bar is raising on these as our systems get more complicated. So Proctor looked around for what do we do about this, and 15288 certainly surfaced as a guidepost, a place to start from. And as we used that to assess our processes, it was very useful in identifying where were we strong and where were we weak. Because all these processes were written in different languages, even though they were all targeting systems development, everybody wrote their different processes down. So the part that was a little bit less expected is that as we applied this analysis, as you guys know, 15288 is an activity description. The purpose of the activities and the nature of the activities, it intimates the data model of systems. It doesn't explicitly call it out. But if you look through that and you start to analyze your existing deliverables, you start to get some insights around those. And what we saw was that any point where we interface with the external world, we were right on. Our artifacts were standardized, they were complete, they were accurate, and they were structured to the optimal level. And we believe the reason why that is that the external interface is very unforgiving. You don't get a redo if you don't satisfy the regulators, right? Or if you specify the wrong drawing for a part, you buy it again. So it's very unforgiving. On the other hand, if you make mistakes in terms of the requirements, you do get a redo on that. You met most of the initiative's objectives, and then you launch another initiative to make those up. It's a little less visible, and we believe that's allowed us to persist with a documentation framework. It's not really a model type framework for the purpose of systems, so the intent leg of the V basically. And so those ambiguities were concerning and also problematic when you're trying to refer down to an area that really is more explicit, like the physical description of the outside world, the digital twin world. And so we started following those digital threads in those documents in hopes of putting them in a systems model. And the truth is, it was unbearably difficult. We couldn't even plot the diagrams of the relationships between the deliverables. We have over 400 classes of deliverables we do to take a product from concept through to distribution. Half of those are technical. It was extremely difficult. And we started thinking about that. We realized the real problem is that this is happening on every project. Not just us who are trying to analyze and improve it, but as the project teams change, people move between roles across business areas, they're solving this over and over again. And so we realized that, ironically, the business process framework of 15288 was guiding a data journey for us. And what we realized is that we had to basically clean slate the data model for specific business functions, and that's the transition that we have to do. So we looked around at what were our options there. We had SysML on one side with 100+ concepts, and then you got linked data on the other, and there's some choices in between. And the problem with this is that, well, first, we respect the works here, okay? So there's nothing in SysML that's random. Everything that's in there, if you learn it and do it, you're going to get a payback from it. Unfortunately, what our business functions want is a disproportionate payback. They want to do a small investment in terms of complexity. They want a huge payback, and that complexity needs to be temporary, okay? So long story short, what we realized to make this work is that we had to make an 80 for 20 type of call. What's 80% of the benefit for 20% of the work to deliver immediate benefits in terms of the data model? And it was quite clear where the productivity had to come from. We had to stop that untangling of the fishing line knot on every project, and we needed to create some kind of systems model to where you could make a change or articulate what the change would be. It could be a change in the feature space or the design components that were allocated to roles in your models. And the system would need to automatically generate the drawings to what those impacts were. And that's across all business functions: advertising, sales, regulatory, manufacturing, product design, distribution, all of them. And the idea is that that's when you lift out and make visible the rational minimum set of work process steps that you need to execute that initiative with excellence. If you can't do that, you're basically figuring out what those steps are by reading through stacks of documents by teams and rooms. Really inefficient process. So the idea is that we need to be able to do this type of analysis across all levels of the Bs for all business functions. That's the way we move fast with initiatives. So to do that, this comes that second tenet where everybody needs to sort of realize that part of what they do is the same thing as what everybody else does. It's analysis of systems. And that these documents that we're producing, hundreds of document types, are basically just views of those systems. So the earth needs to be softened. People need to realize that they have to gravitate towards some common standard to describe the purpose of the systems and the nature of those systems. And this is where William Shandell wrote in and saved the day, solved the key part of the problems for us with his Systematica meta model. And when we first ran across Bill, we were very suspicious that this really could solve everything, but we ran through every business function across multiple sectors over the course of a year. And it worked in every case. In a matter of minutes, the subject matter experts were like, wow, you're describing exactly what I do in much more simple terms. And so I'll quickly walk through the parts of the model. You can talk with Bill deeper conversations about it. But basically part of it, I think, is obvious. You can read books on it, that systems are about satisfying stakeholders who are expecting features from those systems. And those features are delivered as a result of interactions between roles that play out and affect each other's state. Requirements play in here, and that requirements basically call out the behavior of functional roles in response to stimuli they're getting from other systems. And then they in turn change the state of other systems. So basic model that works everywhere, whether or not it's a marketing message where we're trying to interact with the potential buyer of the product to influence the way they perceive it, what's happening in their brains, or it's the product itself. It could be macro, it could be molecular interactions. This type of pattern plays out over and over again. No reason to invent it over and over again. When you're done decomposing the functional roles with this method, you allocate them to physical design components. So these are the materials that you're going to buy, chemical, mechanical, whatever, to assign those behaviors to. Simulations are not left out. There's a place for those. Predicting a change in the design component, how might that impact its behavior as a role, or how changes in the roles might impact the system's ability to deliver against features. So this pattern really worked for us. But to work up and down the whole left side of the model, it really needed to be a fractal, right? So you could have supply chain as a blocks, right? A functional role. It turns out that that decomposes into the same thing. It's a fractal type of pattern, which is exactly what we need, because we don't know if we're going to go down 3 levels or 23 levels as we try to decompose a problem. What's the right number of levels on it? Couplings takes on a different note, and when you start talking about decomposition of systems, it's trying to capture the emergent behavior. So long story short, we realized that this model was the key for us to solve the problem of interdisciplinary communication around the system of systems. And in fact, it captured everything we needed to know about the system. What exists, the nature of the interactions between them, what can we know about the interaction, what's the purpose of the system. There was also an emergent thing that happened too, though. And when these patterns started reaching a certain size and diversity in terms of the discipline's contents that's involved, we started having insights as to unleveraged strengths that we might have, or conversely, knowledge gaps or competitive activity that wasn't addressed, or perhaps areas where we need to invest in more simulations to fine-tune the technologies that we're using. But these things, these patterns, these insights weren't available if you had stacks of documents on the table. We really needed that cross-functional language, a simple model that everybody could pick up and understand in a matter of a few hours. And so that's what we started getting out of this model here. There are some IT architecture implications, and I've seen this in a number of presentations, increasing every year. But there is a place where you need the canonical cross-discipline model. It has to be simple enough for everybody to learn it. I think that's come out through a lot of presentations today. And to avoid the weak link in the chain, I think as David Long talked about, it really needs to be solidly implanted in all the disciplines and fully addressing their needs. And we really like OSLC as a connecting layer because basically you're connecting models to models. If you take the systems level model and connect it to the digital twins below, and the digital twins could be anything. They're regulatory digital twin models too, not just mechanical, electrical, or chemical. So just to summarize, we're talking about a shift from focus on valuing of activities to valuing and focus on assets. Talking about the disciplines, understanding what they do is really common. Half of their job is about manipulating systems, the other half is the subject-specific roles, the domain-specific roles. And then lastly, that canonical systems model, maybe we're not there yet, but we're certainly at the 80-20 point. We can see the benefits, all the different business functions, it's resonating with them, and right now we're engaged in plans to figure out how to scale that up across the remaining business function and other sectors. The part that I glossed over here was this automation piece, being able to click on something and have it automatically show all the impacts. I agree that technology should follow the word process transformation, but if you think about what happened with the Amazon phenom, that was a different thing, right? The technology kind of drove the business process. And so as we've gotten into this, it's taken us a couple years to work through that ability to automatically generate diagrams. In fact, we save no diagrams. We have questions, we ask for them, they generate the analysis, and we discard them. That's made the models much more sustainable, and it also helps to make sure the models are accurate and complete. This has been a boatload of work. We think we're about halfway through it. Some brilliant suppliers we've partnered with throughout this, and in fact, I think you have to see it. Again, back to that Amazon thing. I'd stop by probably go by the Tom Sawyer company, and they will show you. It's also on display in the Reuse company. They're showing how you can start typing a requirement, and the system actually goes and examines the system model in real time, and it knows what you're looking for, kind of like autocomplete in a text message, and it creates real-time binding between every part of that statement and the systems model. We have hopes for that and plans to actually compile those statements, send them over to simulations, send them out to manufacturing systems to monitor whether or not we're about ready to violate those requirements, because it's not a black and white thing. So long story short, this is the summary of the journey. If this is resonating with you guys, reach out to me in between, because we are about halfway there. We don't want to build a technology platform and maintain it ourselves. We really would be much more interested in following the system L journey, building commercializable type of automation and distributing that development cost. So we're looking for development partners along those lines.